How do QKD protocols, like BB84, ensure quantum security? Imagine trying to send a secret message that no one else can read, not even someone with the most powerful computers. That's what quantum cryptography aims to do. It uses the weird rules of quantum physics to keep information safe. One of the most famous methods is called the BB84 protocol. Let's see how it works and why it's so secure. First, think of two people, Alice and Bob, who want to share a secret key. Alice starts by creating a string of bits, which are just zeros and ones. Instead of just writing them down, she encodes each bit onto tiny particles called photons. She uses two different ways to encode each bit, called bases. One is called the rectilinear basis, which uses horizontal and vertical polarization, and the other is the diagonal basis, which uses 45 degrees and 135 degrees. Alice picks a random basis for each photon and sends them to Bob. Bob receives these photons and also randomly chooses a basis to measure each one. If Bob's measurement basis matches Alice's encoding basis, he gets the correct bit. If not, he gets a random result. After all the photons are sent and measured, Alice and Bob talk over a public channel. They compare which bases they used, but not the actual bits. They keep only the bits where their bases matched. This process is called key sifting. Now here's where quantum physics makes things secure. Any eavesdropper, called Eve, who tries to intercept the photons, can't do so without messing things up. Because of the no-cloning theorem, Eve can't make perfect copies of the photons. And because measuring a photon in the wrong basis disturbs its state, Eve's interference introduces errors. Alice and Bob check a subset of their remaining bits for errors. If they see too many errors, they know someone is listening and discard the key. If the error rate is low, they proceed. The security of this system is based on two key principles. First, it's impossible to make an exact copy of an unknown quantum state. Second, measuring a quantum state in the wrong way changes it permanently. These principles mean that any eavesdropper can be detected. Once Alice and Bob confirm their key is secure, they perform some final steps called error correction and privacy amplification. These steps make the key even more secure by removing any small information Eve might have gained. This process results in a secret key that can be used for encryption methods like the one-time pad. The one-time pad is unbreakable if the key is truly random and kept secret. Unlike traditional cryptography, which depends on how hard it is for computers to solve certain problems, quantum cryptography relies on the laws of physics. It offers a way to communicate securely, even against future quantum computers. Protocols like BB84 are a big step forward in quantum communication. They let two parties detect any interception attempts and guarantee the secrecy of their shared key. This makes quantum cryptography a promising tool for protecting sensitive information in the emerging era of quantum technologies.